Okay, so
Yeah,
uh, let's start.
yeah,
I've
sure.
got something to talk about. I'll give you uh, rather a big perspective of what reinforcement learning is.
Yeah, sure.
Uh,
Actually, I reckon I finished my part first because it's kind of basic and boring, and you can leave the interesting part for
right,
the
right,
end.
right.
Yeah,
That's what I was
you agree
thinking.
with
You
that?
can
Yeah,
start.
yeah,
It's not basic and boring.
yeah.
I so the essentially what I wanted from this meeting is to
Yeah,
know what a high school student can, how much the level a high school student can achieve in terms of
yeah,
machine learning, because this is a field which is coming up very fast,
yeah.
and I think in next 3 to 4 years it would somehow be incorporated in school syllabus in the 11th and 12th.
Yeah, actually,
And
CBSE has already incorporated in the 9 to 12 syllabus. From 2021, there will be a new subject on AI.
right. That's very interesting.
Yeah,
And so that's why I was wondering, uh, if more important is the intuition of AI, of machine learning, and but you also need a hang of some of the basic mathematics, and
yeah, yeah,
but
obviously.
that's about it. Yeah, so let's see. I look forward to
Yeah,
our
yeah, sure.
conversation today.
So yeah, let me start then. So it's a short journey from the very rock basic Bellman equations to Monte Carlo and temporal difference. Then we will move on to parameterized functions and then tile coding and then to the actor critic algorithm. Fine.
Right, okay.
Yeah. So let me start. Yeah. So can you see the state value Bellman equation?
Yeah, I can see your screen.
Yeah. So the Bellman equation is the expectation of the rewards that we get. So it is denoted by something like this. E pi means it is under policy pi, and RT1 is the reward at state st plus 1 after we move on from state st to state st plus 1, and the gamma is the discount factor, and gt plus 1 is the future rewards. So it is an expectation under future rewards, like it is the intuition is that it is the probability that we will get these future rewards. So that's the basic intuition behind this. And so if we define what is an optimal policy, so optimal policy, that is a policy which performs the equally or better other than other policies that we get in the environment. This is basically a slide representing how we can compute the state values for a simple grid world environment. You can see that the upper left corner and the lower right corner squares are always assigned the value 0 because they are the ending and the starting positions respectively. And this is how we can compute the state values for the other tiles. So after one iteration, we can see that we have updated the value of one tile. Similarly, we use a uniform random policy, which means that the policy can go either way, either up, down, left, or right with 25% probability each. And after sweeping our entire environment several times, we update the values accordingly. So here's the algorithm. It is nothing but what we just saw, the what is written above the environment. So after several iteration, we can see that the upper left and the lower right starting and the ending positions respectively are starting to affect the other ties. The outermost ties, we can see the innermost ties have all similar value -2, and the outer ties have a value of -1.7. So after many iterations like this, we converge to the actual true state values for this grid world. And looking from the state values, we can gridify our policy with respect to the state values to get an optimal policy. So that's a very, now up till now what we saw was a simple grid world environment. Like it had very less states, very less action states. So what happens if our state action space or the environment is larger? So we cannot loop through every state like we did previously and compute the value functions so accurately. So we have to use a technique called Monte Carlo. So what Monte Carlo does, it estimates a correct value function for each state. Like it plays over many episodes, and each time it encounters a state, it notices the reward we get in that state if we take a particular action, and then it divides it by the number of times it has visited the state. So that
Okay,
way,
wait. Can let me process the information.
yeah.
So, can you repeat that again?
Yeah.
It estimates the true
So
value of the state.
so we have a very large state space. We have a very large action space. So
Right.
how do we sweep over the entire state and action space? How do we do that? It will take a lot of time. A lot of computation will be involved in that. So what we do is we play episodes, and each episode we will encounter some states, right?
Right.
Right.
You
So
you
for
you
those,
using a random policy, right?
yeah, using any random policy, it can go anywhere. So we are noting down that if we encounter this state and we take this action, we get this reward. So each time Monte Carlo gets at some states, it notices the reward it gets. Okay, so it stores that reward and it divides it by the total number of times it has encountered that state. Suppose our agent has encountered a state 3 times. Each time it has got a reward of -1, -2, and -3. So after going through it 3 times, Monte Carlo will say that the value of the state is -1, -2, -3 divided by 3.
Okay.
So we are averaging, like we are using average to get a better estimation of that state.
Right.
Fine.
Okay, that makes sense. Okay.
Yeah. So this is nothing same. And then we move to temporal difference learning. Actually, I have just said that Monte Carlo updates the state values after each episode, right? Like after each episode, you update the state values. But what temporal difference does is it updates the state values just as the environment processes through the episode. Suppose environment is in state 1 and it moves to the agent is in state 1 and it moves to state 2. While it moves from state 1 to state 2, it updates the value of the state 1 just as it gets the reward in state S2. So it is instantaneous. It is the same as Monte Carlo, but it is instantaneous. We don't have to
At
wait
each step, right?
for the yeah, we don't have to wait
Right.
for the episode to get over. We can do it instantaneously. It's the same thing. So if you carefully inspect this
I'll
equation, that is
when I talk about it, I'll actually provide you the intuition behind why we do this, why we do it at every step, and
okay.
what's the logic behind it. So let's wait
Okay.
for it and continue.
Yeah, sure. So the equation we see here. So for the current state, we update the value as the existing value plus alpha. Alpha is the learning rate. Alpha into the reward that we get plus gamma is a discount factor into the state value of the next state minus the state value of the present state. So this gives us a very good estimation of the reward that we get from moving from one state to another state. And the term under the brackets, this is called the TD error. Okay.
Right. Okay.
Yeah. So this is the same thing. So this is the algorithm for iterative policy evaluation using temporal difference learning. So there is just one new step here. So we use this TD update to update the values of the environment instead of what we were doing at policy iteration, where we just using a random policy go through all the states again and again. Yeah.
Okay. Well, let me actually talk about it here.
Yeah.
What how or what's the intuition behind temporal difference. So if you go to that slide where you explain the temporal difference, uh, can you go there? No, the one behind that, one before this one, before this. No, actually,
This
this
one.
is okay. Yeah. So
Yeah.
yeah. So for example, let's assume we are playing chess, okay?
Okay.
And now, if when you're starting to play the game, you don't know which player is going to win, right?
Yeah.
So it's and now let's assume a state which towards the end of the game, where either of one of the player is about to win, and in that case we know that okay, this person is going to win, so we know the exact outcome, we know the exact reward. So
Right.
the idea is the next step that you are taking.
Yeah.
So let's say you are in state ST now, and what you do is essentially you predict the future cumulative reward, which is given by the value function of that
Yeah.
state,
Yeah. Yeah.
which is in this case V of ST.
Yeah.
And what you do now is you go take one step ahead,
Yeah.
and you go to the next state, ST plus 1, and again you predict what should be the future cumulative rewards from that state, ST plus 1,
Yeah.
which is denoted by value of ST plus 1. And in as a consequence of this transition, you get a reward which is RT. So essentially what you did is first you predicted at your present state ST,
Yeah.
you took a step,
Yeah.
and you predicted again.
Again. Yeah.
So you have a new value function V of ST plus 1.
Yeah.
And you have got an additional information here, which is the reward for that transition.
Yeah. Yeah. Yeah.
Getting my point here?
Yeah. 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 Sure.
So
Yeah.
what we are saying now is that the next step, you are getting additional information of the environment of the state,
Yes.
and so you are more confident about the outcome which will happen.
Oh.
So what we are essentially trying to do
Okay.
is take our current state value closer to
Yeah.
the next state value,
Next statement. Right.
plus the reward, which is the actual reward, which is the true reward.
Yeah. Yeah. I get it. Yeah.
So in a sense, we are saying that the next step that we are going to take, we are more confident about the outcome. So it's like the chess. As you go ahead in the game, you get to
Yeah.
know you are more confident about the outcome, who is going to
Next.
win.
Yeah. Sure.
And that is sort of how this came. So
Okay.
because at each step you predict and you take one step ahead, you get an additional true information of reward, and you again try to estimate the future cumulative reward,
Yeah.
and then you subtract these. So this prediction error between your current state and your future state is called the
Yeah.
temporal difference error.
Yeah.
And yeah,
Right.
that's how it came into the motivation
Exist.
behind it.
Right. Thanks.
And I think in a sense, temporal difference is the crux of all reinforcement learning algorithms. Like
Oh.
most of them, like most of the modern algorithms work based on temporal difference learning,
Acha.
and somewhere you will find that term of temporal difference.
Okay. Thanks. That was nice actually. That how we can get our state values as close as possible to the next state values, then
Right.
subtracting the
Because
difference.
exactly, because the next step values are
Uh,
right. That's what we assume.
uh,
And at each step, you're trying to make your present state values closer to the next state, because the next state is correct true values. That's what you are
yeah,
assuming. And as you go ahead in the game, you get the correct true state values for the next one.
yeah, yeah, yeah.
And
So
that's how
nice.
you converge, and that's how we converge the algorithm towards the state values,
Yeah,
optimal state values, right?
yeah. I was going fast in the beginning because I thought you will got bored of all this. Uh,
No, no, actually, this is exactly what I was planning to present. I didn't think you would present this, but
Oh,
that's okay.
okay, fine. Do you want me to go over the previous first slides again a bit, and if you want to ask something, because I went over like through that like hurricane, and do you want to go over it again?
No, no, no. It's fine. It's fine. It's fine.
Yeah,
Fine. I was trying to, this. It's been a while since I've done this.
yeah, yeah.
So trying to make
Sure, sure,
sense.
sure. So let's proceed.
Yeah, yeah, let's go ahead.
Okay. So we ended at this. So this brings us to the Q learning algorithm. So you were talking about the action values. So here we get the action values. So uh, so the algorithm is first we initialize our action values and other parameters. And Q learning is almost like what we did earlier, except we are using action values instead of state values. That is the first difference. And actually, if I have said about SARSA, then it would be better. But and in the update, we are taking a maximum over all actions. We are choosing difference and Q learning and SARSA part. And now it becomes a bit like mathematics. We dive a bit into mathematics because now we are using deep learning to approximate our value functions. We are parameterizing our value functions so we can use neural networks to estimate values, right? So here we go. So the first condition that uh, we can for the function approximator, that it should be compatible with bootstrapping, right? Fine. You know, I think bootstrapping.
No, can you quickly explain it?
Yeah. Sure, sure, sure. If you see the reward, the return, it is like R plus gamma into R2 plus gamma square into R3, like that. Can you relate? Yeah. So
Yeah,
for each,
that's the total discounted reward.
yeah. So we can write, suppose G1 equals to R1 plus gamma G2. We can
Right,
represent 1G as a future G.
right. Okay.
That is essentially bootstrapping. It is a fancy word actually.
So the recurrency, which means
Yeah.
yeah.
Exactly. Recurrency. Right. It's a fancy word. So now we have the how do we compute the gradient? How do we know whether we are approaching towards the optimal value function? So we use the mean square value error, like we do in regression also. So here, actually, in this slide, there is some problems. One problem is, if you notice the mean square value error term, that is mu of s, and in the brackets, you see the v pi s, which means the state value under a given policy. But if you think of it, this is what we need to find out. Then how can we include it in our calculations? It makes no sense. Actually, we have to find out the actual state value. So it makes no sense to how can we get it in our calculations? So how can we get it from before? You're getting me, right?
So here pi is
The
uh,
policy.
an optimal policy, or it could be any
No.
random
It's just
policy.
a policy. In our policy, it's just a policy.
Okay.
It actually the v pi of s. This is the value of a state. Actually, this is what we have to find out. So if we use mean
Right.
squared
Okay.
error, right? We don't know from early on. Then how can we use it in our calculation? We have to find. This is our goal, and that is a problem. That what we can use instead of this v pi of s term. And the second thing is, and it is not a problem, the second thing, mu s is that mu s is the fraction of time we spend in the state while following policy pi. So it is a now we have come to a last part, actually the actor critic part. So this is the last thing that I learned, means this is the most latest thing that I have learned, right? So here we introduce a new concept for average reward. Previously we are using discount. Uh, Now since we have moved on to neural networks, we don't need to use those simple things. Matlab we can use more complex approximators to approximate our rewards. So we can move ahead from bootstrapping. So what we do is we modify our return equation. So instead of the previous bootstrapping, we can use this. And you can ask, how do we estimate the average reward? We can parameterize it and feed it into a neural network, and we will get our average reward like that. So this is our average reward objective. Again, many of the equations in machine learning look almost the same, but they are used in different places. I don't know why, but so okay. Okay. Since from now on, we will be parameterizing our policy as well. Till now, we have seen that we have parameterizing our state value functions, right? From now on, we will be parameterizing our policy. But there is a catch. The thing is, if we use linear approximators, when we will get the final probability of choosing an action, it does not mean that they will sum up to 1. So we use
Okay.
softmax parameterization to ensure that the probabilities that we get they all sum up to 1. So we raise to the power of e, as e always gives positive values. So yeah, so now we have to optimize the average reward, right? So this is the equation.
Right. Yes.
And the interesting fact is that up till this point, all I have learned was
Oh, wait.
gradient.
Go one slide.
Yeah.
Go one slide behind.
Yeah.
Yeah. Policy gradient methods. Okay.
Actually, I will be coming to
Right.
policy gradient method in a while, like in the future slides. So as
So
I was
here,
saying,
wait.
yeah.
What's mu
Oh,
in the
sorry.
previous?
Yeah.
What's mu?
Um, Mu is actually how many times, the fraction of the time for which the policy has been in a state. The fraction of the time that our agent has been in a state. You see, mu
Wait.
has only.
Let's wait. Let's go back a bit. Uh,
Okay.
so here, yeah, okay, you are defining average reward. Okay. Next
Yeah.
slide.
This is a softmax
Here is a
parameterization.
softmax policy, normalizing the policy to 1.
Yeah.
Then you have formalizing. Okay, wait. Go back. Here you have formalizing the goal as an objective. Okay, sorry, continue. Uh, yeah, okay, this is just GT function.
Yeah.
Uh, Next.
Fine. Uh,
Oh,
so it's
okay,
okay
why?
till this.
What is mu
Mu
again?
is a fraction of time that our agent spends in a particular state. Just let me tell you simply. Suppose in an episode, our agent visits 10 states, okay? But suppose there is a state B and it visits 3 times. It visits state B 3 times. So mu is 3 by 10.
Okay, makes
Yes.
sense.
Okay. Yeah. So here we use gradient ascent, but up till now we have only seen gradient descent in basic machine learning and all that, because we have to maximize the average reward. Again, there is some mathematics which I don't actually understand how they compute these gradients and all. So if we compute it, we get it this. So if we move to the previous slide, we see our gradient involves this mu term as well. Okay, but
Right.
these mu terms depends on our policy. Our policy decides how many times we will visit a state, right? So
Right.
actually I don't know the main reason, but they say that it is difficult to approximate the gradient of mu. So via some optimization and all that, we somehow get the gradient of gradient. We remove the gradient from mu, and we get this, the policy gradient theorem. Here you can see that now after optimizing, we have somehow got the gradient of the probability of choosing an action in a given state multiplied by the q value of the state. Actually, now at this point of time, it is slowly developing towards a actor critic algorithms. It is slowly
Algorithm.
developing towards that. Okay. So this is how we update our weights from now on. But this gradient term can further be simplified in a way. So you might ask me, why are we multiplying and dividing by the expectation over actions, right? But since we are following our policy, we would like to get the expectation from our policy only, right? Is how
Right.
will you get the expectation? So, and it provides us with a mathematical advantage as well. So if we modify it like this, we will
It
get
becomes
this
log.
equation. Okay.
Right. Right. Okay.
And then we can write it as this also. We can take the ln. Actually, this is quite like the integration we do in high school only. Like dx
Yeah.
by x,
Exactly.
you
Yeah.
integrate it and you get ln. So this by this series of approximations, we get something which we can compute easily. Okay. Now here is something actually I don't even understand this. So this is the same thing as this slide is the same thing as what we saw earlier, but they have expanded the action value. They have expanded the action value and written like this. And later they are subtracting the present uh, state value, and they are saying that if we subtract it, it now becomes the TD error. But how does it not affect the value of this function?
No. So what we are saying here is that we have a baseline, which is the value of that state,
Yeah.
and we are comparing it to the baseline of that state. So if the rewards that you get are greater than the baseline, which means
Okay.
uh, that action has returned better rewards.
Okay.
And if you do it compared to the baseline, if the rewards that you get are actually less, then it means
Hmm.
that you're not doing good.
Oh, okay. So we can modify like this without affecting the uh, function actually. We can do this.
Right.
And this is a very good diagram I find for understanding this actor critic algorithm, how it goes on.
So this function delta here, which you
Where
define right now,
that is the
it's
TD
also
error.
called the yeah, it's also called the advantage function.
Okay.
So this algorithm, it's by name, it's called advantage actor critic. And this
Okay.
form, this the delta, which is
Hmm.
you're subtracting the baseline value, is the advantage.
Oh, okay. Fine. Actually, if so let me say it once again. We are subtracting it so that if our expected value is less than the actual value, the term becomes negative and a gradient moves that way, right?
Yeah, yeah,
Okay,
exactly.
okay, now I get. So I get it right.
Yeah,
So
yeah,
I'm right.
exactly. So which means if you perform bad compared to the existing,
Baseline.
so it's like in a way, uh, here we had of SW, this term is,
Hmm,
you're using the same network to estimate the value. You're predicting the value from the present state. Okay, which means
hmm,
you think that you will get this many rewards from this state.
uh,
Okay, and then what you do is you take one step ahead
hmm,
and you get a reward R, this one.
hmm.
And can you see the drawings, right? The circles and
Yeah, yeah,
everything.
yeah, yeah, yeah. I can see it. I see it.
Yeah. So what you do is you take one step and you again predict uh, from that state.
Yeah, yeah, yeah.
So you've got an additional information of the reward. And what we are saying is, if this value uh, sort of is it's if it's better than the baseline which you predicted before, you have done a good action.
Yeah.
And so that's actually the TD error.
TDL.
This is the TD error. Yeah.
And this is the algorithm for actor critic. The main part here is how we update the weights. The W is the weights of the critic, and theta is the weights of the actor. So for the critic part, there is no lon equation. Lon, what do you call that? Lon part. And for the actor part, there is a lon factor. Uh, so we have done the critic uh, update for the critic earlier, and the only new thing is that the update for the actor.
Right. Right.
So that's it. That's it.
That's it. Yeah. So let's go back one step. I'll quickly explain what PPO does.
Oh, sure,
So,
sure, sure.
so here in this, so essentially, its PPO is also called proximal policy approximation
Okay.
optimization,
Mhm.
and it is a actor critic algorithm. And the only difference from normal actor critic and PPO is the term of the critic, which is, if you go back again, this sorry this delta term, which we defined, the
Okay.
advantage. Uh, Go back again one slide. So what happens is, it is quite difficult. So this is called delta, right? This
Yeah.
thing, and it is, uh, so here this function v hat is parameterized by the network called W, right? Or theta, W,
Yeah.
right? So what happens is, uh, in this actor critics, normal actor critic, this W is not very stable, which means
Okay.
the update that you do
Yes.
in the W at each step,
Hmm.
it's sort of sometimes, uh, in a sense, it's not very stable. So what I mean by stability is, for example, let's assume we have a hill here, and
Okay.
we have a function, and you're
Okay.
presently, let's say you're presently here. Okay.
Mm-hmm.
And what you do, you're trying to reach the maximum. You said the the gradient ascent algorithm.
Yeah.
So
Yeah.
you're
Yeah.
trying to reach here, but what happens is when you update this term,
Oh.
this update could lead you sometimes, you could just cross over the whole maximum and reach here.
Oh.
And
If we
once you
use a
reach here,
small learning rate,
then it takes time. So essentially, what PPO does is
Yeah.
it restricts this movement update to uh, so there is some mathematics involved. So that is
Acha,
called, I won't go into it. It is called KL divergence. And
okay.
what you do using this term is you limit the update, so that you
Okay.
don't overshoot here, like once you go above or somewhere here.
Okay.
So you, because then you calculate that using this term, that this update is going to take you here, and then you add a threshold that you can't go here, you can only go until this, like in some neighborhood of this somewhere.
Acha, acha,
And
acha.
that's how PPO is able to achieve uh, converge quickly compared to normal advantage actor critic.
Okay.
And but then it's only about the mathematics. How do you prove? So what they have done is, in this paper of PPO, which was published in 2017, they have actually proved that by using the scale divergence term, you can restrict the update, and they have shown that it increases the stability. That's it.
Okay.
That's the new thing in PPO. And so what we are doing here is we are learning this TD error. This happens at each time step.
Uh,
So what it means is, we are in state ST. You go to state ST plus one,
mm.
and then you update this
Yes, yes.
network, the critique network.
Mm.
So that's why it's on policy update, which means you are updating while you are playing the game, while you are doing the task.
Yes.
So what soft actor critic does, which is soft actor critic was published in 2018,
Okay.
and what soft actor critic does, it's an off policy algorithm.
Okay.
So in a sense, it uses some random policy, it stores in a buffer, and then it trains both these networks, the lon network, which is parameterized by theta, and this network, which is parameterized by w,
W.
uh, outside. So what it does, it samples from the buffer that it has stored using the random policy that it has used.
Acha.
So in a sense, what soft actor critic does is it stores everything inside uh, inside a buffer, and sample out from that buffer, and using that sample they train this w and theta,
Okay. Okay.
and they add this what, the KL divergence, which is done in PPO. So in a sense, you can see how actor critic evolved. Is this is the baseline actor critic.
Okay.
Then you have an algorithm called DDPG, if you might know.
I have heard of it,
So
but I read it in just the
DDPG
turning.
stands for, yeah, it stands for deep deterministic policy gradient, and it's the same thing here. Just it's the difference is it's done off policy, which means you train it outside, while not while you're doing the task, but somewhere else. Like both the you one network decides the policy, and you complete the policy, and then you train it, you store it in a buffer and sample out from the buffer. So the idea here is that uh, you are removing the temporal dependency between each state. So for example, I am currently in state ST, I go to state ST plus 1, and from ST plus 1 I go to ST plus 2. So when you're learning while you are playing, which means on policy,
Mm.
there is a temporal dependency, time factor, which means your
Okay.
previous state depends on the state, sorry, the next state depends on the previous state.
Uh,
So
yeah.
there's a bond between states, which means your ST
Mm.
plus 1 would be dependent on ST,
Still.
and that factor somehow uh, leads does not converge well,
Okay.
and that's why off policy algorithms are always better than on policy algorithms. So the idea is you sample out from a random buffer, which are not temporally connected to each other,
Okay. Right.
and that's That's how you learn. Because I think machine learning in general, if you see, uh, your training data needs to be random and independently distributed. The more wide and variety of things you
Yes,
have in the
yes.
training data, the better it is for the network to
Yeah, yeah.
converge. And that's what is done in off policy learning.
Yeah.
You don't have that temporal dependency.
Fine.
And that's the reason off policy learning are always efficient compared to on policy learning.
Okay.
So hence PPO, active A3C are less data, or take more data, take more samples, take more episodes compared to DDPG or soft activity, which converge quite quickly. So that's the difference between those two.
Okay. Yeah. Fine. What do you
But
guys
yeah,
use
I
in
think
your problems?
so. Right now, we most of the community it uses either PPO or soft activity, because those are almost well known and optimized. You will find the code as well. So many people have implemented it, and those are the state of the art. But uh, that's for basic reinforcement learning. But now the communities, everyone is shifting towards unsupervised learning. So how can we use uh, that the reason for that is that to train any simple game, for example Atari game, it takes 5 or 6 million frames to learn from that game.
Hmm.
Which is actually uh, not very good. We humans, if we see, we can play 5 or 10 times and we can learn from that. Whereas a network, if it starts learning, it takes 5 million frames. So the learning is not very efficient. And that's what now the research, most the community is moving towards, how to make this learning efficient, how to use less data, less frames to learn from that. And for that, they are using mostly unsupervised learning methods, and they combine it with this reinforcement learning, which is PPO or soft activity, to see if you can reduce the training time, training data needed.
Fine. This is the end. I don't have any more slides.
Okay, no,
Acha,
that was interesting.
give me a honest review. How well was it?
No, it was good. I think you understood. I think you understood the maths behind it.